Hello?
Yes, hello.
Okay, now we hear. Welcome to our ENS webinar on fusion today. Today we would like to welcome Professor Carlos Hidalgo from National Laboratory of Fusion, CIEMAT, from Spain. And the webinar was initiated by our member, Spanish Nuclear Society. And the webinar name is Towards a Fusion Reactor, Integration of Physics and Technology. Professor Hidalgo is currently leading the Experimental Plasma Physics Division at CIEMAT, and he is author of more than 200 peer-reviewed publications on solid-state physics and plasma physics. So we know that just recently, European research roadmap to the realization of fusion energy has been recently updated. And Professor Hidalgo will describe the physics approach oriented to predict the behavior of burning plasmas with confidence, and the engineering approach with the goal to control and improve the technical performance of magnetic confinement devices. Professor Carlos, maybe before we start, we initiated this webinar with polls. So we prepared together three polls for you, three questions for you. And the first question, what we would like together with Professor Hidalgo to put you is: are you aware of the challenges confronting nuclear fusion as an energy source? Let me see if I can launch these questions, because I have now some. Yes. Okay, so all the audience, what we have today 34 attendees following this webinar. I would like to ask you to click the answer what you think is the right answer for you. Are you aware of the challenges? Okay, I will wait another 20 seconds. Okay. So for the moment, the answer is yes, and 74%. 70 people attending this webinar voted. Thank you very much for your activity. Professor Hidalgo, maybe we ask one question more to warm up the audience.
Yes, of course.
Okay, so the second question, what I have here is: are you aware of the challenges? Are you aware of the EU strategy towards the development of nuclear, the development of nuclear fusion? Are you aware of the EU strategy towards the development of nuclear fusion? Yes, no, not sure. There are three answers possible. I will wait another 15 seconds to let you click the answer. There is no correct answer here. So every answer is correct. Another way. It's changing. We have still 30% that didn't vote. the answers are very polarized. So we have 38% which are aware, 38 which are not, and 23% are not sure. So I think this is the right moment to present, to give the presentation on the fusion and the EU strategy towards the development of this. Okay, so I would like to invite you now to Professor Hidalgo's presentation.
Okay, thank you very much, Emilia. Can you see my first slide on the screen?
Not yet. Did you activate your slides already?
Yes.
No, I don't see. Ah, no.
No.
Yes. Yes, fantastic.
Okay, then thank you very much, Emilia, for the introduction and also for the invitation. It is, of course, a great pleasure to join this activity in a remote way. So I will talk about fusion, a reactor integration of physics and technology. And I will, okay. So my first question is very general. What makes human beings really unique in nature? And of course, you might argue that that really makes us very unique is our verbal communication skills. And actually today we will today we will use our verbal communication skills to exchange ideas on nuclear fusion. Or you might argue that really makes us very unique is our capability to build very complex instruments. And also today, we will discuss complex instruments to produce fusion energy. But in addition to our verbal communication and our capability to build complex instruments, there is one more ingredient that I would like to emphasize today that makes us really unique, and is our ability to imagine and to shape the future, making use of science and technology. And I think that the goal of getting nuclear fusion probably is a fantastic example where we humans are shaping the future of having the energy of the universe working on Earth. Let me start talking about something very general, fusion and fission, because these two energy sources share the same physics ingredients. Is the famous Einstein expression energy equal to mass times the speed of light squared. In fission energy, we have heavy nuclei that we split in smaller size nuclei, and in this process there is a small change in the mass. In fusion, we start from light elements that we fuse together to get a much heavier element. Also, in this process, there is a change in the mass, which is very, very tiny, but once we multiply this small delta m by a huge number, the speed of light squared, we get a huge amount of energy. And actually, fission are one of the most efficient energy sources we have in nature. If we want to have fusion, we need to introduce a very basic concept what we call the fourth state of matter, a plasma. And for sure that most of you are fully aware that if we start with solids, let's say solid ice, if we increase the temperature of the ice, we get water. If we increase even more the temperature of the water, we get a gas, steam. And if we increase much more, now the temperature of the gas, we remove electrons from the atoms and we get a kind of soup of positive and negative particles. This is what we call a plasma. Of course, on Earth, plasma is not the most common state of matter, but in the universe, it's very different. More than 99% of the visible universe is in a state of matter, in the state of plasma. So if we want to have nuclear fusion on Earth, we need a kind of recipe that includes the following ingredients. First, we need to heat our light nuclei, deuterium and tritium, to very high temperatures. High means temperatures in the order of 100 million centigrades, which is pretty high. This is about 10 times the temperature we have in the core of the sun, our star. Now we need to confine our plasma using high magnetic fields. The magnetic fields that we are using in fusion are in the order of few Teslas. Few Teslas means magnetic fields about 100,000 times the magnetic field we have on Earth. And in order to confine plasma with this magnetic field, we build a kind of magnetic bottle that we call TOKAMAKS and accelerators. So the recipe to have nuclear fusion on Earth looks rather simple. You just need to heat your deuterium and your tritium to very high temperatures to allow the fusion that give heavier elements, alpha particles, and fast neutrons with an energy of 14 megaelectron-volts, and helium, alpha particles with an energy of 3.5 megaelectron-volts. What are the basic ingredients of these magnetic fusion devices, in particular tokamaks? You need to have a kind of vessel with a torus shape that will contain the plasma, and you need magnetic fields to create the magnetic trap. In the case of the tokamak, we have not only the magnetic fields produced by external coil, you have also plasma current flowing in the plasma. So the final magnetic trap is a combination of external magnetic fields and the magnetic fields produced by the plasma itself. If we move into the second family of magnetic traps to confine high temperature plasmas, what we call accelerators, they are in principle very similar to tokamaks. So we have also coils that usually are a bit more complex to produce magnetic fields. But the main difference is that now the magnetic field is only produced by external coils. The contribution of currents flowing in the plasma is completely negligible. One of the good points of the accelerators, where magnetic field is fully defined by external coils, is that it promises steady state operation, which is very important for fusion reactors. So we know that we need to heat matter to very high temperature to produce plasmas. We know that we need to build complex instruments magnetic traps that we call TOKAMAKS unaccelerators to confine the plasma at high temperatures to allow fusion. So what is the European strategy towards nuclear fusion? One of the first ingredients, very crucial pillar, is the so-called ITER project. That probably you are fully aware of this project, which is under construction in the south of France. ITER is a tokamak. So the magnetic field is produced by external coils and the plasma current flowing in the plasma. First plasma operation of ITER is expected by mid-20s and full performance in the mid-30s. ITER will prove the scientific and technical viability of nuclear fusion. Of course, next step is to build a device that is able to produce electricity. And this is what we call demo. The concept should be defined in 2030 and constructions will happen after ITER full performance. As I mentioned before, if we have fusion of deuterium and tritium, we produce very energetic neutrons. And these neutrons will interact with the reactor materials. So it is very, very important to be sure that the mechanical properties of our materials will survive in a very extreme environment, which is the environment of a star on Earth. So here we have two very important projects that we call DONES and IFNIF. These are devices that will produce fast neutrons to test the properties of fusion-relevant materials. Of course, today we have a very important input from research which is ongoing in existing facilities in Europe and all over the world, as well as theory for understanding the behavior of matter in extreme conditions. And all this research is supporting ITER and also supporting DEMO and also supporting the development of this family that I mentioned before, the accelerators that are similar to TOKAMAKS, but there is an important difference that the magnetic field, the magnetic trap, is only defined by external coils. Just to give you an idea of the order of magnitude of the size of these devices, in this slide you can see the characteristics of major accelerators and TOKAMAKS under the European flag. We have what we call the ASDES upgrade tokamak in operation in Germany, or the JET tokamak, the flagship of the European program, in operation in the United Kingdom. And you can see now the size of ITER, this experiment under construction in the south of France. You see magnetic fields are in the order of few Teslas. In the case of ITER, the magnetic field will be 6 Teslas. If we talk about the volume of plasma, between JET, which is the biggest tokamak in operation all over the world, we will jump from 90 to 840 cubic meters. So the size, the volume will increase by a factor of 10. You look at the axis, the major radius, you see the major radius of the 16 devices in the order of 2-3 meters. ITER will jump to 6 meters. And then below you see the typical sizes of accelerators are quite much smaller than the size of tokamaks. This is reflecting that from the technological perspective, it is much more complex to build the magnetic trap for accelerator than building a tokamaks. So accelerators are a kind of one generation in terms of size and performance compared with tokamaks. Where we are, as you know, human beings, we are trying to have the energy of the universe in our hands since quite many years. So what do we need to reach to have a reactor? Well, we need to have not only a very high temperatures. I mentioned before, we need temperatures in the order of 100,000 centigrades. When the temperature is so high, usually we talk not in terms of degrees, but we talk in terms of energy. So these 100,000 centigrades means energy is in the order of 10, 20 kilo electron volts. But in order to produce energy, we need also to have good confinement of our plasma, which is confined in these magnetic bottles. And this is characterized by a very important number, the energy confinement time. And also, in order to produce energy, we need to have enough density of our deuterium and tritium. And then all together, density, confinement time, and temperature give us this yellow region that is the area that we need to have ignition, means a device that is sustained by the energy produced in the reactor and is providing electricity to the grid. ITER, our important project in the European strategy towards nuclear fusion, is right here, yes, in the yellow area. An important line in this diagram is what we call Q equal 1, QDT equal 1. Q equal 1 means that the energy that we have to invest in our system to keep our plasma under fusion relevant conditions, this energy is equal to the energy that we get from the fusion reaction. And actually, existing experiments are moving towards the ignition area, and existing devices, in particular the JET TOKAMAKS in operation under the European flag, was very, very close to the Q equal 1. So we can transform these conditions in this very fundamental expression that tells you that if you want to have a reactor, the density times the confinement time times the temperature should be larger than 5, 10 to the 21 meter minus 3 kilo electron volts, second minus 1. So far we were getting very close to 10 to 21, so we still need a factor of 5, roughly, to jump from existing experiments to ITER, to the yellow area. Well, a factor of 5 looks small as compared with the progress during many, many years of research and technology development, but still a factor of 5 will be a tremendous jump, because we will move from existing conditions to a fully reactor relevant scenarios. Because we have ITER as a key ingredient in the whole program, let me show briefly a view of ITER in a 3D perspective. This big torus where we have a set of coils, toroidal and poloidal coils, to produce the magnetic trap together with the magnetic field produced in the plasma. Because ITER is still an experiment, we need to have many windows to look how this star is behaving in terms of performance on Earth. This is one of the ports that will be used to install diagnostics, to look the radiation emitted in the infrared or visible range, to be sure that we don't have any damage inside the vacuum vessel, where you can see now in gray some kind of protection elements, beryllium, and in the bottom in dark gray we have tungsten protection tiles. This is the area that we call the divertor, and this is the area where we will get huge fluxes, energy fluxes to the materials. Fluxes that, as I will mention in a minute, are very close to what we have on the surface of the sun. Europe has a strong commitment in the construction of ITER from many different perspectives. We have European teams working in the development of the heating tools to reach plasmas with the right temperature and with the right density that is needed for fusion. We have also many European teams working in the building of plasma diagnostics. That means complex instruments to monitor the characteristics and properties and dynamics of plasmas. We have many European teams involved in the development of the magnetic coils that we need to confine properly the plasma emitter. So yes, ITER is a key element in the European program with huge contributions from different perspectives, from the most basic physics to the most advanced technology. But as I said before, in Europe we have also a very important pillar in the fusion program that we call accelerators. Closely related to TOKAMAKS, but now because the whole magnetic trap is produced by external coils, these coils, magnetic coils, are much more complex. So the technology is much more demanding. Here we have the key element, the driving force for the accelerator program in Europe, the so-called Waldenstein 7X accelerator, which is in operation since 2016. And it was a great, and it is a great challenge in terms of technology and physics. Present experiments has proved that we are able, from the technological perspective, to build the technology of coil that is needed to have magnetic surfaces, the magnetic trap, to confine the plasma. And this can be done with an accuracy of more than 1 in 100,000. So it is unbelievable, the level of improvement in technology for the construction of fusion devices. So what are the key ingredients of a fusion reactor? You ask this question to a physicist, and I have to say I am a physicist. Then a physicist will start talking about the physics optimization that you need for a fusion reactor. A physicist will start talking, oh, we need to build a magnetic trap which is able to optimize the energy confinement, because this is one of the key elements in this triple product that I just mentioned. A physicist will start talking about transport of particles of energy. We'll start talking about the role of fast particles. Remember, a fusion reactor will be fully dominated by fast particles. Also, we'll start talking about heat power loads in the vessel components and how to optimize the physics to minimize these heat power loads. A physicist also will say, oh, we need to develop all the physics understanding and physics tools to control the density of deuterium and tritium in the reactor core. A physicist will emphasize, oh, we have to be very careful with impurities, because the plasma at the end will interact with the vessel inside the reactor, and then we will have release of impurities, and we want, of course, to minimize these impurities, because impurities will reduce the stored energy because of radiation losses. A physicist also will emphasize that In the fusion reaction, where we have deuterium and tritium, we are producing fast neutrons, but also we produce alpha particles, fast particles. So we need to develop the physics understanding and control tools to control helium densities in the core. You can ask the same question now to an engineer. And then an engineer probably will start talking about performance and technology optimization. An engineer will say, well, if we want to have a fusion reactor, we need to be aware about tritium self-sufficiency, because this is what we need, deuterium and tritium. And tritium has a lifetime of about 12 years, so tritium must be produced in the reactor. An engineer will emphasize, look, if you want to have a reactor, you should be aware of the influence of fast neutrons, 14 mega electron volts, in the properties of materials, functional, structural materials. Even an engineer might argue that we want to have high temperature superconductors in a fusion reactor to reduce the cost and to open new possibilities for operation at very high magnetic fields. An engineer will emphasize that, look, we need to talk about cost. What is the cost of the fusion reactor? What is the expected component lifetime? What tools do we have for remote handling? Because we will need to modify and to repair components. An engineer for sure will put the magic word safety. Yes, we have tritium, so you need to have the right tools for tritium inventory. Be careful about tritium permeation, because tritium should not escape from the reactor. And this is an area which is very much connected with social acceptability. So at the end, if we want to have a reactor, we need to ask the question both to physics and technology. And we need this integration of optimization from the physics perspective and from the technology perspective. So at the end, what happens if we aim for optimization, where we talk about remote handling, where we talk about availability, and where we talk about performance of the plasma and confinement time? And then, of course, the consequence of this integration will have an impact, important impact, in the final magnetic topology, where we want to optimize the physics, but also we want to do this optimization integrating technology. What are the main fusion challenges? And as you can imagine, these challenges are including physics and technology. One of the first challenges is very much connected with physics. You want to have a fusion reactor, you need to have the right plasma scenarios where we have fast particle physics, where we have to control impurities, where we need to avoid, and this is very important for tokamaks like ITER, disruptive phenomena. And of course, the actions from the physics perspective is to have an understanding of critical plasma issues and validated theory and modeling. This is a huge area and fascinating area of physics, but of course I don't have time right now to go into many details. Just let me give you an example. One of the great discoveries in the last 20 years is that when we are pushing the plasma to that extreme plasma conditions that we need to have in a fusion reactor, because we have very steep gradients in temperature, in density, in pressure, we have huge number of instabilities. But even we have a huge level of turbulence, the system can be self-organized. even when we are very far from thermal equilibrium. And this self-organization, driven by instabilities, allows us to have what we call zonal structures in the plasma, affecting the whole dynamics of our fusion reactor. This kind of self-organization that was predicted in fusion plasma actually is something that we have seen in nature since many years ago. These are these zonal structures observed in planet atmospheres. Just to give you an idea of time scales, how science is progressing, this prediction about self-organization in fusion plasmas is from the mid-80s, and it's a pure theoretical prediction. We have to wait about 20 years to have a fully direct experimental evidence of this self-organization. This was done first in Japan and later on in my home country, Spain. 20 years. That's the time scale we need in Spain to have a good Rioja wine. So advancing science needs time. And this area of self-organization is a very fascinating area of theory and research right now, where the role of fast particles, that is the key ingredient of a fusion reactor, is under discussion. Very fascinating theories, predictions. Still, validation is missing. This gives you an idea of how physics is progressing and what are the time scales that we need for having a theory, for having a validated theory. A second challenge is the problem of heat exhaust and plasma phasing components. The plasma phasing component that we have developed for ITER should work. This beryllium plate I mentioned before, tungsten plate in the diverter. But the plasma phasing component that we will need for a demo reactor is still an open challenge. Here, the ongoing actions are including a program supporting ITER. Look for alternative solutions for phasing components, including, and this is an area of research right now, including liquid metals, and of course, playing with the magnetic configuration in a clever way to reduce as much as possible heat loads on plasma phasing components. This is a great challenge because we need materials you can lay on the surface of a star. Just to give you an idea of order of magnitude, the heat flux that we have in the sun surface, in yellow in the screen, are in the order of 100 megawatts square meter. The heat flux in green that we are expecting in the fusion diverter will be in the order of 10-20 megawatts per square meter. And these fluxes will remain for a long time because at the end, the fusion reactor hopefully will be steady state. Eventually, in a fusion device, even ITER, for a very short time scale, we might have what we call disruptive phenomena. And in this case, the heat fluxes will be even above the heat flux we have on the sun surface. So this gives you an idea of this important challenge where both physics and technology are deeply involved. The third challenge is materials. I have mentioned this point before. We have fast neutrons, 14 mega electron volts. And we need to be sure that the reactor materials will survive enough time because we have to be worried about the cost. So here we need to have and these are one of the key actions in the European program, a neutron source development. A neutron source for 14 megaelectron-volt neutrons that will allow to test the mechanical properties of materials. Again, remember, we have deuterium, we have tritium, we get fusion, and we get these fast neutrons and fast alpha particles. These fast neutrons, 14 megaelectron volts, will interact with the material, with the atoms in the stainless steel, in the structural materials. And then this energy of the neutron is so high that atoms will be removed from the equilibrium position, leaving what we call a vacancy, a kind of structural defect. Eventually, these atoms might move somewhere else in a position that is not expected, is what we call interstitial. So we need to understand how these structural defects will affect the mechanical properties. This is a very important technological aspect. Of course, also we want to have very advanced simulation of materials, so we can do models of materials in a fusion relevant environment and try to predict what will be the behavior, and also validating models with real experiments. And this is the point where we have this key program done with this very strong collaboration with our Japanese colleagues, IFNIF, DONES. These are particle accelerators where we will have high energy deuterons and also high currents that would allow to have significant fluxes of neutrons to explore regimes with damage, structural damage, relevant for a fusion reactor. So we hope to reach what we call DPA, these displacements per atoms per year in the range of 2050. And of course, in this facility, we will do the irradiation of our material, but at the end, we will do a mechanical test to see how mechanical properties are affected. And the fourth challenge, I will call this as a pure technology, tritium self-sufficiency. This is a key ingredient in a reactor because tritium must be produced in the reactor. So in the reactor, we have the deuterium and tritium that will fuse together to produce a neutron, fast neutron, 14 megaelectron volts. So we need to multiply the neutrons using neutron multiplier. This can be done with beryllium or with lead. And we need a system with lithium to produce tritium. So the reaction of the fast neutron with lithium will produce tritium that must be recovered back to the fusion reactor. We need also to have a coolant. It could be helium, or it could be also water. And this is the essence of what we call breathing blankets. Some of these concepts will be tested in ITER. We need to look at the technology of lead, lithium loops, tritium extraction, corrosion, inventory, safety, and so on. And this is a very important element as well of the fusion program to be developed in ITER. So if we look into the fusion challenges, I hope I convince you that we have physics and technology, and they go together. So the optimization must be done in a loop connecting physics and technology. I mentioned at the beginning that the physics of fission and fusion is very similar, is the Einstein equation E = mc². But from the point of view of technology, there are plenty of areas where we have synergies between these two communities. Of course, materials is a clear example. Right now, we are testing materials for fusion using fission reactors, remote handling technologies, heat removal tools, modeling of neutrons. We are using tools developed by the fusion community, and also many other areas, including instrument diagnostics or quality control and nuclear safety. There are areas where fusion has a fantastic experience. Of course, the main drive, as you know, for fusion is to deal with the energy problem. And I think before I finish my presentation, I should remind something that probably you are fully aware. No roses without thorns. We have different options for energy, which is the blood of our society. We got burning fossil fuels that we are using today. This is the blood of our present society. In green is easy. This is a plus for this kind of technology. But in red is that we have enormous quantities of CO2. And this goes into the problem of climate change, as you know. We might go into the area of renewables, sun, wind, hydro, biomass. Of course, in green is that now we reduce a lot the CO2 emissions. But in red is that we have large fluctuations. And also in red is that this energy is very diluted. Or we can go into the option of nuclear fission energy. In green is that we have very little CO2. This is very good. But in red, we have the problem of public acceptance, safety and waste treatment. And last but not least, we have fusion energy. The good point is that this is a massive energy source and sustainable. But in red, as I have mentioned during my presentation, is that we still have very important scientific and technological challenges ahead of us. And this is the key point I wanted to send as a message. Yes, we need fusion energy, but we need to push the existing program on science and technology. So I go back to the beginning. What makes human beings really unique? Yes, fusion is an example where we are shaping the future to have the energy source that drive the universe on Earth. This is a very great challenge. A great challenge where we need to have full integration of physics and technology, but also a fascinating area where I'm pretty sure in the coming years we will see many important discoveries in ITER and coming devices to have in the second half of this century nuclear fusion as a reality on Earth. So thank you very much.
Thank you very much, Professor. It was a very interesting presentation, and I'm very grateful also for this comparison between different technologies, which none of them have disadvantages, I would say. Thank you very much for this. We have 2 questions coming from the audience from Mr. Ulrich Thiele. So I will read 3 questions, apologies. So I read the first question. So we start with the questions and answers session. We will have 8 minutes for closing the webinar. So the first question is, how much electrical energy will be needed to start ITER or the demo, in watt or watt hours?
Well, I think this is a very good question. as I mentioned before, here we have a magic number, which is the so-called Q value, which is the ratio between the energy we need to put to invest in our system respect to the energy we get from fusion energy. Just to give you an example in numbers, in the case of ITER, the investment in energy or in power will be in the range of 50 megawatts. And the energy that we are hoping to get in ITER will be 500 megawatts. So it means that we will have in ITER an amplification of a factor of 10. You put 50 and you get 500. Of course, ITER is not a reactor. In an ideal reactor, you will turn off all the external heating and the reaction will be sustained by the fast particles. So ideally, in a reactor, the Q factor will be extremely high, close to infinity. But in the case of ITER, this number is 10, so means you put 50 megawatts and you get 500 megawatts.
Okay, thank you very much. There is the second question of the same person from Mr. Thiele. How will the activated material of the first wall have to be treated or separated from the biosphere to avoid radiation harms of the environment?
Well, I think this is also a very interesting question because, yes, any material exposed to neutrons will be activated. The key point is when we talk about sustainable energy means that the waste that we produce to enjoy energy in our life, in our quality of life, is managed by the generation using this energy. So any waste produced in any energy source that can be managed by the generation means time scale of 100 years will be called sustainable energy. So the choice of the materials in a fusion reactor is done in a very clever way to have this activation time scale acceptable. Acceptable means 100 years. This is a big difference between fusion and fission. In fission, the waste material could last thousands of years. So this is the problem of fission, is how to be sure how to deal with long time scale waste, activating materials. So in the case of a fusion reactor, time scale will be in the order of 100 years. But of course, this activation is something that you cannot avoid because you have fast neutrons.
Maybe one question from Max Brugger. Are there proliferation issues?
No. This is also an important point. In the case of a fusion reactor, we start from light elements, deuterium, tritium, and we get these fast neutrons and the fast alpha particles, helium. So what we have as a result, the as material in a fusion reactor is helium, and helium is an element without any proliferation issues. So this is also an important point when we talk about difference between fission and fusion.
I have a question from Nathan Patterson. What is your opinion on some of the smaller fusion reactor programs and the path ahead? Do you think that they are competitors or partners to reach the end goal?
Well, I think that yes, this is also a very good question because today I have emphasized the European strategy towards fusion. And the European strategy is based on the deuterium tritium and the use of TOKAMAKS accelerators. But in the last years, we have seen new groups fully supported, some of them by private funding, that try to explore different scenarios, not necessarily based on deuterium tritium. And I have to say that I think this is very good. This is reflecting the interest of a very wide community towards fusion. I have to say that maybe because I am fully involved and deeply involved in the European program, as far as I know, the DT strategy is the most credible way to have fusion reactor on Earth. But I'm happy to see that these other groups are trying to explore alternative scenarios using proton, boron scenarios and others. But my personal opinion is that the DT approach is the most credible one.
Okay, thank you very much. We are having already 2 p.m., but maybe we can put the last 2 questions which are appearing on the list. So one question is from Henry Ormus. I'm not sure, yeah, maybe you will be the kind of repetitiveness of what you said, but what is your estimation of when the plasma can be sustained to really produce electricity?
I think, again, this is an important question. We are dealing with one of the most challenges projects that human beings can imagine, is to have the energy that sustains the universe on Earth. Following my first remark about what really makes us very unique, the human beings will never stop our imagination and our capability to say the future using science and technology to have the energy of the universe on Earth. But this is a so fantastic task that although the progress up to now is amazing, we got almost Q = 1 in existing devices. The time scale to have a fully operational fusion reactor is not for tomorrow. I mentioned in my talk that it should be in the second half of this century. So we are like building a cathedral where a generation is building the basement, and a next generation will enjoy the view of a great building. So these time scales, I know that some people think are, oh, this is a long time scale. And I always say the same. And what? Remember, building a cathedral is not trivial. And building a fusion reactor is a dream that we will keep moving until it's fully successful. Even this is a work for my daughters, for your daughters, or whatever.
I hope that you're still with us. There's the last question that I will read you aloud, and this is a question I think a bit philosophical, social. Why should public acceptance be higher for fusion than for fission? Both are strongly connected to atoms and radiation.
Well, I think the public acceptance is a must. We are in a democratic society. And a democratic society means that at the end, decisions are taken by citizens. In a democratic society where we are, citizens should be well informed about the risk and about the benefit. I think this is the essence of democracy. So that's why public acceptance, my opinion, is very fundamental. And we scientists, we have to explain the facts as they are. And at the end, it should be the society that take the decision.
Yes. Thank you very much, Professor Hidalgo, for this webinar. This is the series of webinars what we organize regularly every month dedicated to different technical and scientific subjects. The record of this webinar will be available on our YouTube channel under the ENS webinar, and the next information on the webinars will be published on our LinkedIn profile of ENS for the moment. Thank you very much for listening to us, to Professor, and stay tuned. Thank you.
Thank you very much for the invitation.
Thank you.
Bye-bye.